Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. With this video, we are going to have solution to be determined for the wave equations that we know from the knowledge of electromagnetic field theory. As in the previous video, we have got it very clear that the microwave now can be delivered from one device to the another device through a simple metallic hollow tube called as rectangular waveguide. So for the metallic hollow tube, we have the cross section of a rectangular shape there. Now in the unbound media, the wireless media, we can say here we had the wave equations that were governing the behavior of the electric and magnetic vectors here. Let us see how the behavior is affected when we have this microwave inside a certain cavity filled up with the dielectric, most possibly the air there. So here we start with our topic, where to have solution for the wave equations, we consider the rectangular coordinate axis here. So very first of all, we shall be taking the three axes. So let us say this is the x-axis and this is the y-axis. So these are both a part of this plane of the paper, and the mutually perpendicular to x and y, the third axis we consider to be the z-axis here. Now these are the three axes. The z-axis is actually perpendicular to the plane of the paper, coming out and going inside the paper. So for the two-dimensional case here, we show it a tilted line. So basically it is having 90-degree angle with that of the x and 90-degree angle with that of y-axis here. So the intersection of the three is the origin here. So we take the rectangular waveguide to be matched with the original origin point here. So one corner we get it matched to this particular position, and now this will be the simple orientation we consider along the propagation for z direction here. So this is the one end we have shown. So as per the previous diagram, we have the broader dimension denoted by small a and the smaller dimension denoted by small b here. A can be regarded as the breadth of the waveguide, inner dimension. B is width of the rectangular waveguide, again the inner dimensions here. Now wave propagation we consider in the third direction, that it is perpendicular to the two dimensions small a and small b here. Now to see the solution of wave equations, we shall be either confined to that of the time domain or that of the frequency domain. So depending on the convenience, the sinusoidal equations or the frequency domain equations into the complex form we shall be showing here. So initially we have the two wave equations. So one is for electric and another is for the magnetic here. So for the electric, the wave equation into the frequency domain is represented as del square capital E is equal to gamma square capital E here. And we have del square capital H is equal to gamma square capital H. So here these are the two equations we have expressed, where we have gamma is equal to square root of, we have j omega mu in the bracket sigma plus j omega epsilon here. So where gamma is also expressed as alpha plus j times beta. So here we have gamma to be the propagation constant. Alpha is regarded as attenuation constant, and beta is regarded as phase shift constant. So these are the two equations that we have represented in terms of frequency domain. So as we have the omega corresponding to that of the angular frequency. So with the help of the complex representation for J, we have the frequency domain representation, I can say. In terms of time domain, we originally had the equations of the form where we have del square capital E minus mu epsilon d2 capital E divided by del T square is equal to 0. Whereas for the magnetic field intensity component, we have del square H minus mu epsilon del 2H by del T square is equal to 0. So when we regard the time domain equations corresponding to the electric and magnetic vectors here, these are the second order time differentials, whereas we have del square, this is the delta, or also we can say the Laplacian operator. This is the differential spatial operation here. So let us regard this to be the equation number 1, this to be the equation number 2 for the time domain representation, and for the frequency domain representation we can regard this to be the equation number 3 and equation number 4 here. Now in this representation, as we switch from time domain to the frequency domain, the time differential of partial type del t is replaced by j omega here. So omega relating to the frequency, t for the time domain. Here it is the only change. We can represent it in the both ways here. Now these equations, equation number 3 and equation number 4, are called as vector type of the wave equations, and these two equations are found to follow the Helmholtz equations. So the Helmholtz equation in the standard form are shown to be del square psi is equal to gamma square psi, where this del square can be expanded as del 2 by del x square added with, we have del 2 by del y square further added with del 2 by del z square, where x, y and z are the three spatial coordinates. So these are the spatial coordinates taken under rectangular coordinate system. So let us see this Helmholtz equation in general, that is showing the del square, that it is the Laplacian operator. The differential with respect to the space parameters is equal to gamma square, the same psi vector here. So this is into the frequency domain. Let us say this is equation number 5. Now we have expressed the del square here. So if you take psi to that particular function, the psi will be the coefficient under the partial differentiation with respect to small x, y and z for each of the term onto the right hand side here. So let us say this is equation number 6, and this addition is to be regarded as gamma square psi function according to the Helmholtz equation here. Now by the method of separation of variables, let us assume that solution can be of the form of psi will be equal to capital X of small x, capital Y of small y and capital Z of small z here. Let this can be regarded as equation number 7. So this is the solution that has the term capital X of small x. Small x is the spatial domain parameter here. So this is a function of small x coordinate only. Whereas capital Y of small y is a function of small y coordinate only. And the third one after this, capital Z of z is a function of z coordinate only. Now when we make a substitution the substitution of equation number 7 into equation number 6, and we have a division to the resultant by equation number 7. So this is by the division here. So here we have the substitution to the above equations denoted. We get the form of the equation as 1 upon capital X in multiplication to d2 capital X divided by dx square added with 1 upon capital Y d2y by dy square 1 upon capital Z into d2 capital Z by dz square. So this is equal to gamma square. Let us say this is the new equation, equation number 8 it is. So now when we see at the first term, so in the first term we have capital X in the denominator. The capital X is derivated with respect to the small x. So this term involves x and derivation with respect to the x. So it has to be result into a constant value. Whereas in the second and third term of the left hand side, we find the similar form that we have all the terms associated with the y coordinate here. So the differentiation with respect to the y itself is again a constant. And here also this is all the terms with respect to the z and z only will result into the third term to be constant. So this is equal to gamma square here. So now the representation of these three constants corresponding to the x, y and z can be made with the help of the representation of, here we have small k suffix s squared here, small k suffix y squared, small k suffix z to be squared along with the negations here. So because of this we can get the new form of the previous equation number 8 to minus kx square minus ky square minus kz square is equal to gamma square. Let this can be the equation number 9 here. Now from the previous equation, if you separate out the variables corresponding to only x, only y and only z, so that time we get the differential equations as d2 capital X by dx square is equal to minus kx square into capital X. So let us say this second order differential equation is of number 10. In the similar fashion, we obtain d2 capital Y by dy square is equal to minus ky into capital Y by equation number 11. And we have d2 capital Z by dz square is equal to minus k suffix capital small z here into capital Z by the equation number 12 here. So these are the three equations I outline, which are the second order differential equations. Now as they are related to only x, y and z, we are not necessary to denote it by partial differentials, but a complete differentials we can switch to in this particular derivation. Now the general form of solution corresponding to these partial differential equations converted to the full form of differential equation of order 2 can be of the form, for the first equation, that it is capital X is equal to capital A into sine of the function k suffix x into x added with capital B into cosine of k suffix y. So here we have capital B into cosine of, we have k suffix small x into x here. Let us say this is new equation number 13 it is. In the similar fashion, we have the solution for the equation in terms of small y is equal to capital Y is equal to c sine of ky into y added with capital D into cosine of ky into y here. Let us say this is equation number 14. Now we have the last equation for the variable z here, capital Z is equal to capital E into sine of kz into z added with f into cosine of kz into z here. Let us say this is equation number 15. So in all these three equations representing the solution corresponding to the x, y and z dimension parameters here, we have the sine function and the cosine function in multiplication to the constant values capital A, B, capital C, D and capital E, F here. Determine the values of these constant represented A, B, C, D up to E, F here. We have the complete solution corresponding to the equations that we have started to have solution. So now combining the total solution into the form represented for the Helmholtz equation in terms of the vector psi here, we can simply make capital the psi here representation having a product of the first square bracket that involves capital A sine of kx into x added with capital B cosine of kx into x. So this is the square bracket completed. We multiply it with another square bracket with respect to the variable y that has capital C as the constant into sine of, here we have kyy added with capital D a constant into cosine of kyy. So this square bracket is also completed, and this is in multiplication to the third solution that has capital E sine of kz z added with capital F cosine of, we have kz into z here. So let us say this is the equation number 16 it is. Now in the representation for a complete solution for psi here, we have the propagation of the wave into the waveguide under consideration that it is rectangular waveguide. Conventionally assume the positive z direction there. Now the gamma we have represented to be the propagation constant. So the propagation constant inside the waveguide here can be simply denoted as gamma suffix g here. So as into the equations previously, the wave equations, we have the term of gamma square here. The gamma suffix g squared is nothing but the gamma square added with k suffix x squared added with k suffix y squared here. So this is simply is equal to gamma square added with k suffix c squared here, where k suffix c is nothing but the square root of kx square plus ky square here. So here we have considered gamma to be the propagation constant in the unbound condition before it has entered into the waveguide here. This is the propagation constant once the microwave has entered the waveguide there, and these are the two variables we have discussed before corresponding to the spatial coordinates x and y that have the variations into the electric vector and the magnetic vector only. The z parameter, the z vector we have considered for the direction of propagation of wave there. Now this equation that we have denoted gamma suffix g square can be regarded as equation number 17. Now we shall be discussing the criteria to have lossless type of propagation of microwave. For lossless type of propagation of microwave, we require that the gamma square should be equal to minus of omega square mu epsilon here. So therefore this results into the lossless type of gamma suffix g is equal to plus minus square root of, we have omega square mu epsilon minus kc square. Let this can be the equation number 18, and these are the three cases that we shall be discussing one by one to analyze this wave propagation. So we take case number 1 here. So for case number 1 we obtain no wave propagation. The no wave propagation we obtain because we have omega c square mu epsilon is equal to kc square, and this results gamma suffix g is equal to 0. So this particular condition can be treated as the critical condition. Critical condition, or we can say this is the cut-off propagation. Beyond this situation, the wave propagation cannot be taken place here. Basically, the gamma is equal to alpha plus j beta. So ideally, we don't want the value of alpha here. So alpha, the attenuation measurement, should be equal to 0, and we want gamma to be equal to j times beta. We want the change of the phase that is not possible into the criteria we have selected. That is why for the case number 1 we obtain no wave propagation here. Now for the case number 1, the cutoff frequency we must define. So the cutoff frequency is denoted by f suffix c, and it is obtained as 1 upon 2 pi in multiplication to under root of mu epsilon, and this is the ratio in multiplication to square root of kx square added with ky square. Let this can be the new equation number 19. So after this we have to discuss the case number 2. So in case number 2, there it will be the microwave, and the microwave will be having a propagation possible here. So the propagation is made possible by keeping omega square mu epsilon to be greater than that of the kc square here. In the previous case we have equated the two, therefore there it was no wave propagation, no microwave propagation especially we can say here. So in this particular situation, gamma suffix g is equal to plus minus j times beta suffix g here. Substituting the value of beta suffix g, we can get it to the form plus minus j omega square root of mu epsilon in multiplication to the square root of 1 minus fc by f here. This is to be squared here. So this is the new equation we can regard equation number 20. So in this particular case, case number 2, it is very necessary that the operating frequency for the microwave should be greater than that of the cutoff frequency of microwave propagation. Now let us address the third and the last case that we treat to be the case number 3, where there it will be the attenuation of the microwave. The attenuation of the microwave is obtained when we have omega square mu epsilon less than that of the kc square here. So this results into attenuation of wave. So here the corresponding propagation constant gamma suffix g is obtained as plus minus alpha suffix g. There it won't be the phase change, there it will be only the attenuation possible, the real part that we have obtained. So it is plus minus omega under root mu epsilon in multiplication to a square root of, here we have fc by f squared minus 1 here. So here we have the operating frequency f in general case, that it is lower than that of the cutoff frequency fc. Hence we obtain the attenuation of the wave here. So considering all these three situations, we express the final solution to the Helmholtz equation form by psi is equal to, here we simplify the first bracket, capital A into sine of kxx added with capital B cosine of kxx here in multiplication to, here we have the second bracket, c into sine of kyy added with capital D into cosine of kyy here, and this multiplication is with the exponential e to the power minus j times beta suffix g into z parameter here. So here, as z is the direction of propagation that we represent in the last equation here, equation number 22, we have the harmonic, we can say, but the representation in the terms of phase change here. So these are the variations corresponding to the x and y spatial dimension here. So this was all about the solution of wave equations, considering the rectangular waveguide to be the medium to carry the microwave from one device to that of the another device here. By having simple Moore derivation, it will be very much clear that the ideal type of the transverse electromagnetic wave mode of wave propagation is not possible in single conductor transmission line as like the rectangular waveguide. Hence, we have to go for either the transverse electric TE mode or the transverse magnetic TM mode of wave propagation. So by the next lecture, we shall be analyzing certain equations regarded to that of transverse electric mode, TE mode. So I hope you are definitely getting the concepts very much cleared with respect to the microwave engineering topics. So for more details and the topics as like, you can subscribe to Ekeeda channel. Thank you.